Welcome back to module 6. We are presenting quantum adiabatic theorem, and one thing we tried to emphasize here is that when there is a dynamical evolution going on in quantum system, just before initiation of the dynamical evolution, the system is in a stationary state. It can be in a single state, let us say ground state. But after the dynamical evolution is turned off, immediately after that point of time, the system is not in the stationary state. System is in a non-stationary state, and that non-stationary state has to be expressed in terms of the linear combination of the stationary states available for the system. And that is exactly what we have done here. This is general consensus of general way of doing the calculating the exploring the quantum system in the which is using TDSE, time dependence Schrodinger equation. So what we are saying is that just before the expansion, it was in the stationary state, and the stationary states are given by H naught. But immediately after the expansion, we cannot give more time after the expansion. It is just exactly immediately after the expansion of the box, the particle is in non-stationary state, and that non-stationary state, which means that I may have population in different states. That is why it is non-stationary. If it is in the population staying in the same state, then it is not a non-stationary state anymore. But if the population are staying in different states, it means that all states are going to contribute. It is more like a superposition, and the moment I have superposition, it is called non-stationary state. So this non-stationary state will be defined as linear combination of all stationary states present at that time, at that LT distance, and LT distance, which means that HT Hamiltonian will give me that stationary states. So those stationary states may be occupied, and we need to find out the population of each occupancy of the states. So that is the basic idea which we have to follow, and we have clarified that due to this non-adiabatic due to this adiabatic change, due to this temporal change from 0 to t, the total accumulated phase would be this one for each nth state. Each stationary state is accumulating a temporal phase of this kind, because ET is changing, ENT is changing. So instead of writing this expression, this entire thing, we will assume that theta n, we will define a quantity called theta n. Theta n is actually minus I by h cut 0 to t E n t dash dt dash. That is the theta n. So basically this entire integration is theta n. So we will just replace this by theta n. Okay, I does not have that. So it is theta n is actually 1 by this. So in that case, I will be able to write down I theta n t, a phase factor, total phase factor, which is accumulated by the nth stationary state at that time at LT distance, for the LT distance for the LT dimension of the box. Each stationary state is accumulating the phase. This is the phase. Each stationary state wave function is given by this at that time, and its contribution to the total wave function, which is a non-stationary state. So what we need to do now, as usual, for any Schrodinger's way of solving the problem, we have to insert this one to TDSE to get this unknown Cn part, to find out what is the population each state contributing, how much each state is contributing to the non-stationary state of the particle. So that's exactly what we are going to do right now. For the subsequent mathematical derivation, further we will write down few things. We will write down that as a result of slow temporal variation of the Hamiltonian, this at time t, which is immediately after the process is turned off, this eigenvalue equation is valid, psi nt. This eigenvalue equation is valid, and this is one thing which we have already said, that before the expansion the eigenvalue equation was h0 psi 0 equals en0 psi n0, and after the expansion I have now, this is t, this is instead of 0 I have now t, instead of 0 I have now t, instead of 0 I have now t, and instead of 0 I have now t, immediately after the expansion is turned off. So this part is valid, and when this is valid, then we assume that at time t, which is LT, is the distance, the dimension of the box. For this dimension of the box, the all this psi n which we have written, it is actually the states here, not states here. These are not these states are given by h naught, but these states, stationary states, are given by ht, that is the Hamiltonian at time t. So those states are orthonormal to each other. So I can write down that psi m t, we will use Dirac's notation, n t equals delta mn, which is nothing but 1 when m equals n, and it is going to be 0 when m not equals n. So they remain, so those states remain orthonormal at any at that time. So at time t, immediately after the process has been turned off, those stationary states remain orthonormal. So these are the facts we have considered to solve this problem, and now all we need to do is that this is the unsurge, which is a trial wave function. We have to insert to this TDSE and get the solution, which means that we will be looking for what the expression we have for Cn. Cn will give me the population of each state, each available state. So let us look at the derivation. We will first insert this to the right hand side. So sorry, left hand side. So left hand side, for left hand side what I get is that I h cut partial derivative with respect to t psi t equals I h cut, now summation over n, this is d Cnt. This is not a partial derivative anymore because Cn depends on only on time, but this is partial derivative because although explicitly we are not showing it, x depends on the variable x, the psi depends on variable x. So it should be written like this way, psi x Lt. Instead of writing like this way, we are just writing psi t. Okay, so we should not get confused what is the notation, what does it mean by this notation, and that is why we are using the partial derivative here. But Ct depends on time, so that is why this is total derivative we are considering here. Now this is psi n t e to the power I theta n t plus summation of Cnt partial derivative psi nt e to the power I theta nt plus summation of C nt psi nt, then I theta nt e to the power I theta nt. Now this is going to be also the not going to be the partial derivative, it is going to be total derivative, because theta n depends on the energy, and energy depends on, does not depend on x, energy depends on only LT. So that's why this is going to be total derivative. So this is what I get. So if I simplify little bit further, I will get summation of d cnt dt psi nt e to the power I theta nt plus I h cut cnt partial derivative of the wave function e to the power I theta nt plus, now what I have is that I have I here and I have I here. So what I'll have is summation of cnt psi nt, then minus h cut, it will become minus h cut because of the I multiplied by I, then the derivative of this theta nt, this phase part, multiplied by e to the power I theta nt. So this is the left hand side. Right hand side, one can insert here right hand side is going to be ht psi t, which is nothing but ht summation of cnt psi nt e to the power I theta nt equals ht. Now ht acting on psi nt, we have previously said that ht acting on psi nt will give me ent psi nt. That's the time independent Schrodinger equation, the eigenvalue equation at time t, which is immediately after the adiabatic process is turned off. This eigenvalue equation holds. That's why we get the different eigenstates at that time. And so I can write down, this is nothing but following, this is nothing but cnt, then ent psi nt e to the power I theta nt. Okay. Now because this theta nt is nothing but minus 1 by h cut 0 to t ent dash dt dash, one can write down that d theta nt dt is 1 by h cut ent. One can write down this. So basically integration is now converted to its derivative form. From this derivative form only we get this integration. So we are getting the derivative form. Once we get this derivative form, one can write down this ent is nothing but minus h cut derivative of theta nt with respect to time. So this can be inserted here. We have ent, this can be inserted here, and what I get is that the right hand side finally transformed to cnt, then minus h cut d theta nt dt psi nt e to the power I theta nt. That is what I get from right hand side. because it is TDAC, left hand side and right hand side should be equal. So, this part and this part should be equal, and if we make it equal, what we see here is that this part and this part will be cancelling each other, and in the end what I get is I get I h cut summation of d cnt dt psi nt e to the power I theta nt equals minus of I h cut summation of cnt psi nt e to the power I theta nt. This is what I get. I and I h cut will cancel out. So, finally, I get after inserting that trial wave function, which is also called unsurge, that we get this expression, and we have to further reduce it, and we will be able to reduce it further by multiplying the entire expression by psi. So, we will multiply by psi star mt and make use of not orthonormalization condition. So, I will multiply this one by psi mt. So, I'll just rewrite this one as follows. I will write down as, and then integrate it over the spatial coordinate, which is psi mt, then this is going to be psi nt integration, then I have this factor I theta nt equals, here also I will do the same thing. I will multiply from the left hand side by this psi m and then integrate it over the spatial coordinate e to the power I theta nt. So, this is what I get to reduce it by multiplying by this complex conjugate of the psi m, because we are going to make use of the orthonormal condition. Orthonormal condition we have seen, it is this is the orthonormal condition. This is becoming 0 when m not equals n, and this is becoming 1 when m equals n. So, we will make use of this, and this is a trick which we use many occasions to reduce TDAC. So, this is a very common trick. So, this expression, this final expression will reduce down. Every other terms will be 0 because of this term, except for when n equals m. So, I get only this term surviving dt e to the power I theta mt. This term will be surviving. On the other hand, right hand side I cannot do anything because this is with respect to derivative. I do not have any trick for the derivative yet. So, I have to keep it as it is, minus n cnt psi m e to the power I theta nt. And what we will do, we will just take this one on the right hand side, and finally we will be able to write down dcm dt equals minus cnt summation, this is integration, this is bracket notation, dt e to the power, now I, then this is going to be theta nt minus theta mt. That is the final expression we get. So, in order to reduce this expression, what we need to do, we need to find out this expression. If we get this expression, because theta m theta n has already an expression. Theta n, we have seen theta n t is nothing but minus 1 by h cut 0 to t e n t dash dt dash. This is the integration represented by theta. So this part is known. The this part, if we get an expression, we'll be able to reduce the expression further. That's exactly what we'll do. We have now this expression already given, and we need to know this one. So in order to get this one, what we'll do, we will first take the time derivative of this expression. This is the eigenvalue equation at time t immediately after the adiabatic process is turned off. So we will take the first derivative with respect to time. We get ht psi nt equals, with respect to time, it is going to be ent psi nt. So it is going to be now, first it is going to be the first term would be partial derivative, because Hamiltonian depends on x, plus wave function also depends on x, that's why it is going to be partial derivative, equals, this is going to be total derivative, because energy depends on the length adapted at that time t. So it depends on time only, and this psi nt remains, plus I have now partial derivative ent, partial derivative of psi nt dt. So this is the expression what we get. Now if we multiply, again we'll use the same trick. If we multiply from left hand side, if we multiply, then what I get is that psi m star, we are multiplying from left hand side and integrating over the coordinate space. We will have this psi mt, then this, then psi n t. So this is one integration, plus we will have psi m t h t n t partial derivative equals, now this one is going to be e n t dt psi m psi n t plus e n t psi m t dt. So this is the expression finally we get, and we have to note that this is the integration over coordinate space, which means that this is nothing but 0 to some L. I will consider this is the coordinate space, x is varying coordinate space, then psi m star t, then h, then psi n t dx. That's the integration. So this integration, this is the meaning of this Dirac notation. So we will go ahead and we'll be able to reduce it, because H is an Hermitian operator. It can actually act, because it's Hermitian operator, the property of Hermitian operator, we know that it can act from right hand side. So it can actually act on this, and if it is acting on this, then what I get from this is that this part is nothing but E m t, then psi m t psi n t dt. So, this part can be written like this. And if this integration can be written like this way, then I can replace this part here, and if I replace this part here, I can replace this part here. So, what we'll do is following. I have this one which can be written as now psi mt psi nt, this integration as usual. Then I have this emt, then psi m equals this energy derivative remains to be same. This is the total derivative. This is then psi mt psi nt plus ent this is going to be n partial derivative. So, what we get now if we consider that m not equals n, if m not equals n, this integration will become 0, this goes 0 if m not equals n. Then I can write down this psi m partial derivative. This is nothing but this part can be written as integration of psi mt then partial derivative of the Hamiltonian, this divided by ENT minus EMT. One can write it down because this part and this part we are clubbed together and we are finally writing down. But this can be written only when m not equals n. So, and this is exactly what we have here, this part. So, we can insert it, and if we insert it, what we get here is that d cmt dt equals, I have to write down cm t then psi m t dt minus all other summation where n not equals m, that is the condition we have selected. It is going to be cnt then psi mt then psi nt, this integration divided by ENT minus EMT part. So, what we have done, this entire summation we have divided into two parts, one part for n equals m, another part for n not equals m. Okay. For n not equals m, we have written this part, entire part, but for n equals m, what will happen if n equals m, then this is going to be cm, that's we have written one term will get n equals m, and then this is going to be m, but n equals m. So, this part is m and this part will go 0 because theta m minus theta m will be 0. So, that part will not exist anymore. So, finally, we have found that the expression can be reduced to this, and once we have reduced to this expression, we will be able to do now adiabatic approximation. The adiabatic approximation is following. Adiabatic approximation. Adiabatic approximation assumes that because H is changing very slowly, one can write down this to be negligible or 0. So, this part becomes 0, and if this part becomes 0, I get the expansion coefficient equals minus CMT psi mt dt. This is the approximation. Under adiabatic approximation, we get this expression, and once we get this expression, one can now integrate this expression as follows. This is going to be dCm by Cm, integrate it from Cm0 to Cmt time equals minus 0 to t time. This is going to be dt dash. So, we have again distinguished the variable for the integration and the limit for the integration. So, limit is showing that I am looking at the integration from 0 to t, and if I do that integration, then immediately I get this value CMT at time t, which is immediately after the adiabatic process is turned off. This will give me the population at the mth state, that will be controlled by Cm0 at time t equals 0. What was the population multiplied by e to the power? So, this part is going to be the ln. So, we have e to the power I, we write down I gamma m t, where gamma m is defined by I 0 to t dt dash. This entire integration comes in the gamma m. There is another phase factor we have included. So, this is the solution. So, what we are getting is that the expansion coefficient for each state is given by this expression. It will depend on the initial population at that state, and it will depend on the another phase factor which is going to be introduced due to this adiabatic change. So, we can now write down all everything all together. This was the wave function of the stationary non-stationary state immediately after the it started at 0 time, it ended at time t, and immediately after the adiabatic process ended, I would like to know the wave function which is representing the particle, but the wave function is no longer a stationary state wave function, it is a non-stationary state wave function, and a non-stationary state wave function is represented as a linear combination of all stationary state available at that time only, at this t time, which is for the box LT dimension. And that depends on this particular phase factor which we have seen already, and now Cn has a particular value. Now, for a general, this part is for any m state. So, this can be also converted to n state also, any n state. So, I can convert it, and the moment I convert it, I will be able to plug that in, and if I plug that in, I will be writing down explicitly. This is going to be C1, this n can vary from 1, C1 t psi 1 t e to the power I theta 1 t plus C n t psi n t e to the power I theta n t plus, like this way we are adding all the terms to represent this non-stationary state of the particle, and we know that each expansion coefficient will be given by this. So, I can write down as C1 0 e to the power I gamma 1 0 gamma 1 sorry not gamma 1 0 gamma 1 t e to the power I theta 1 t, that is the first term. Then all terms will be added. Then I am explicitly writing Cn term also, Cn 0 psi n 0 oh, there is a psi n here, this is psi 1 t, psi 1 t, then e to the power I theta n t. So, this is psi Cn 0, then it is e to the power I gamma 1 t gamma n t, and then psi n t e to the power I theta n t plus all these things, all the terms will be added to represent the stationary state wave function. Now, if we consider the initial condition was the population before t equals t less than 0, before the process started, we assume that the particle was in the nth stationary state. If the particle was nth stationary state, and that means the population is going to be then 1. So, Cn 0 is going to be 1, remaining all other C 0, which is C1 0, C2 0 at 0 time, all are going to be 0. So, as I can see that these all terms will be 0 except for this term. So, in the end what I get is that this psi t is nothing but psi, and this is going to be 1. So, it is nothing but psi n t e to the power I gamma n t, and then e to the power I theta n t. That's the way it reduces. So, it shows that if I start with nth stationary state of H 0, the finally the particle will stay under adiabatic approximation. This may not be true for if I do it quickly. The expansion happens very quickly, but the expansion, because the expansion happens very slowly, the particle remains in the nth state of Ht, discrete nth state of Ht, but it stays in the nth state. That means the energy state will be defined by this time, but the wave function accumulates two different phases, and the definition of these phases, this theta n is called dynamical phase, and this gamma n is called geometric phase. We will look at what is the meaning of these different phases in the next class.